Hey everyone, and welcome to This Explainer. Today, we're diving straight into the seriously cool physics and the frankly insane software behind modern directed energy weapons, or DEWs. For decades, we've seen these laser systems on the big screen, right? Just zapping targets instantly with these pristine glowing beams of light. But taking that cinematic imagination and turning it into a battlefield reality has been full of some truly incredible engineering hurdles. So, in this explainer, we're going to break down exactly what stands in our way and how throwing artificial intelligence into the mix is finally bridging the gap to make these sci-fi systems a reality. Okay, let's jump right in.
So just a simple question to kick things off, why don't our real-world lasers look and act like those sci-fi blasters? Why aren't we just pointing and shooting at a target with a flawless, uninterrupted beam of light? Well, the physics of generating a high-energy laser, whether that's a solid state, a fiber, or a chemical laser, is actually something we've largely mastered. We've got the power. The massive gap between our expectations and reality isn't really about creating the laser itself, it's about what happens to that laser the absolute millisecond it leaves the barrel of the weapon.
All right, Section 1, the invisible enemy, our atmosphere.
And that brings us to the core problem here. The primary villain standing between our laser and its target is Earth's atmosphere. See, in the vacuum of space, a laser travels perfectly. But down here on Earth, our atmosphere basically acts like a dense, constantly shifting funhouse mirror that actively fights to tear the laser beam apart before it can even do any damage. In a perfectly clear environment, a high-energy laser maintains a beautifully focused beam. It hits the target with maximum intensity. But the second you introduce fog, dust, or smoke, that pristine beam is subjected to what we call aerosol-induced scattering and absorption. The energy just spreads out and dissipates. So what starts as a highly lethal, perfectly focused beam essentially turns into a scattered, absolutely useless flashlight by the time it reaches the target.
So let's break down these atmospheric villains a bit more, because they are relentless. First up, we've got aerosol and dust scattering, which literally bounces the light particles right away from the target. Then there's fog and rain absorption, where water droplets just soak up the laser's energy. But the third one, this is wild. Thermal blooming. As the laser passes through the air, it literally heats the air up. This creates a localized temperature shift that acts like a lens, actively defocusing and distorting the beam itself. And finally, turbulence and wind shear cause beam wander, meaning the beam is jittering all over the place. Just imagine trying to hold a laser pointer perfectly still on a moving target a mile away while you're standing on a vibrating platform right in the middle of a windstorm. That is the daily reality of directed energy weapons.
Moving on to Section 2, the hardware fix, adaptive optics.
So to fix this absolute atmospheric chaos, engineers initially went with a classic hardware solution known as adaptive optics. This was originally developed for astronomical telescopes, and the basic idea is honestly brilliant. You fire a lower power probe beam at the target first. A wavefront sensor then measures exactly how the atmosphere distorted that returning light. Then, this incredible piece of hardware called a deformable mirror physically changes its shape, bending and shifting its surface in real time to apply the exact opposite distortion to the outgoing high-energy laser. It essentially pre-distorts the beam. That way, when the atmosphere inevitably messes with it, the beam actually snaps back into perfect focus right as it hits the target.
Now, the crucial point here is that adaptive optics hardware absolutely works, but we run into a massive limitation. We're dealing with mechanical hardware trying to keep up with an incredibly chaotic battlefield. Deformable mirrors rely on physical actuators, and those take time to move. When you're trying to track a hypersonic cruise missile or a swarming drone that's maneuvering erratically while the wind is simultaneously shifting all around you, mechanical systems are pushed to their absolute breaking point. The target is simply moving too fast, and the atmosphere is changing way too rapidly for pure hardware to ever keep up.
Which leads us to Section 3, the AI beam control revolution.
Enter AI predictive beam control. This is the real game changer. Instead of just reacting to the atmosphere with physical mirrors after the fact, we're using machine learning algorithms to process all of that chaotic environmental data instantly. The AI doesn't just react, it predicts. It anticipates exactly where the target will be, how the wind is going to shift, and how that thermal blooming will behave, and then it adjusts the laser's focus in mere milliseconds. The system literally has to process the math of that funhouse mirror at the speed of thought, just so the weapon can fire at the speed of light.
According to the Defense Science Review, you can see exactly how AI tackles these specific battlefield nightmares head-on. Challenge number 1, fast-moving or swarming drone threats. The AI mitigation, it autonomously prioritizes which target to hit first based on threat level and predicts their flight paths. Challenge 2, that atmospheric attenuation and turbulence we just talked about. The AI provides real-time sensing and predictive correction, optimizing the beam shape before the hardware even fully moves. And challenge 3. What if the enemy gets smart and uses reflective coatings? The AI can actually adaptively switch frequencies to find the most damaging wavelength for that specific material. It's a completely dynamic, totally intelligent process.
All right, let's look at Section 4, AI in the kill chain.
So how does this AI brain actually function step by step when a real threat appears on the radar? We have an integrated conceptual model of the AI-governed directed energy weapon kill chain. The whole thing hinges on AI-assisted decision support right in the center. It sits at the very heart of the entire process, interacting with every single phase from the exact moment a blip appears on a sensor, all the way to assessing the damage after the laser fires. Let's break down exactly what the AI is doing in each of these critical steps.
First up is detect. The AI filters out sensor clutter, birds, clouds, noise, to find the actual threat. Second is track. The AI stabilizes the pointing jitter and calculates the predictive optics. Third, identify. Is it a friendly aircraft or a hostile loitering munition? The AI discriminates the target instantly. Fourth is assign. Say you have a swarm attack. The AI allocates power and cooling resources, deciding exactly how much energy is needed for each target. And finally, engage. The AI manages the atmospheric attenuation and thermal blooming we discussed, holding the beam precisely on the absolute most vulnerable part of the target.
And the main thing you should take away from this is the sheer mind-bending speed of this entire process. We are truly talking about the speed of light versus the speed of thought. This entire 5-step kill chain we just walked through, it happens in the literal blink of an eye. Human reflexes simply cannot detect a drone swarm, calculate the atmospheric turbulence, adjust a deformable mirror, and allocate battery power in a fraction of a second. It's impossible. The modern weapon completely relies on the AI's predictive capabilities to actually hit and destroy a maneuvering target. Which brings us to a really tricky part of all this. Section 5. The human in the loop. Relying on this hyper-fast software brings us to a profound crossroad. We've talked about the physics, the hardware, the code. Now we have to talk about the human element and the very real operational dilemma this technology creates. As the Defense Science Review states, the integration of AI-driven beam control and autonomous target evaluation introduces both opportunity and risk. A human-in-loop architecture remains critical. This highlights a massive tension in directed energy development right now. On one hand, you absolutely need the AI to aim, adjust, and fire fast enough to defend against hypersonic missiles or drone swarms. But on the other hand, military doctrine and basic international safety norms demand that a human being oversees the system to prevent misidentification, manage escalation, and just ensure accountability. We're building systems that act way faster than humanly possible, yet we must fundamentally keep a human in control.
And that leaves us with a pretty provocative thought to ponder. As these defensive systems become more advanced, more autonomous, and frankly increasingly necessary to counter modern threats, should we ever let an AI fully pull the trigger at the speed of light? The physics are largely solved. The software is catching up fast. But the ultimate decision of how we actually deploy these sci-fi realities, that remains entirely in our hands. Thank you so much for joining me for this explainer. I hope this gave you a clear, structured look into the incredibly fascinating world of AI and directed energy weapons. Keep learning, and I'll catch you next time.
Knowledge grows through sharing. What are your thoughts on today's topic? Let me know in the comments below. Don't forget to subscribe as we continue to grow together.